back. Today's topic is behavior of conductors and dielectrics in electric fields. In the last lecture, we have discussed about the dipoles, the electric field which is created by a dipole. We have also seen potential due to a dipole, and also we have seen what is the torque which is experienced by the dipole when it is placed in an electric field. Apart from this, we have, in the last SLT, we have also discussed about differences between conductors and insulators. We have seen this particular concept, and we have also seen what actually is a dielectric and how it is different from an insulator. We have seen these things in the last video lecture. Now, in the present video lecture, we will be concentrating only on the concept of polarization and how to compute polarization in a given specimen. So I hope that by the end of this lecture, you will be able to describe the concept of polarization and determine the extent of polarization in a given specimen. We will do simple calculations on that. Now, moving ahead with the concept of polarization. Now let us suppose if I consider any dielectric material and the dielectric material is having a permittivity of epsilon and it is situated in an electric field of E which is applied in a direction normal to the slab. So what is the meaning of this? So I'll take a slab which is nothing but a 2-dimension or a 3-dimension type of material, and this material is made up of some dielectric material which is having this is the permittivity of this dielectric material, and I am placing this dielectric material in an electric field. This is the electric field. So this electric field is normal to the surface of the slab. So this is normal. This is the surface of the slab and this is normal. And the intensity of this one is epsilon. Now, this is the dielectric material which is having a permittivity of epsilon, and this is the electric field intensity in which this dielectric is being placed, which is acting normal to the surface of the dielectric material. Now, assuming that the material can be polarized, so the impact of applied electric fields, what happens is there will be a concept of polarization which we have already discussed. So normally there are two types of dielectric materials, polar, non-polar. In a polar dielectric materials, already there will be dipoles which will be reorienting themselves, or otherwise if there are no dipoles, then it is considered as a non-polar dielectric material. Then there is a chance of origination of a dipole. So anyways, dipoles will be created, that is what our assumption is, and these dipoles will be oriented in this fashion. Now this is, suppose this is plus and minus, this is the direction of electric field, so you will be getting a concept like this. And so everything will be oriented in this fashion. See, this is which has been shown here. All things, they have been now oriented in this fashion. Now if you carefully see, the effect of field is to polarize the dielectric material, including the atomic dipoles throughout the volume of the specimen and aligning them in the direction of the electric field. Now EA is considered to be the applied electric fields. So when you are applying this electric field EA, then automatically what happens is, consequent to neutralization, equal and opposite charges in the dielectric material, which we call them as dipoles. Ultimately, charges reside on the left and right hand side of the slab. So finally what happens is nothing but they will get neutralized. Finally, you will be getting a negative charge here, and finally you will be getting a positive charge. This is an assumption that finally this is the orientation of the charges, and this is the net charge on the sides of the slab. Okay. And these are separated by a length which we call it as the length of the slab, represented by the symbol L. Okay. Now, assuming that the area of cross section, this area of cross section is area of cross section is A, and the length of the slab is L. So what is the volume of the entire specimen which you are considering? It is A into L. Okay, so that's what I have mentioned here. Volume of the specimen is A into L. Okay, now what is the dipole moment in the volume? You know the dipole moment is always equal to charge into length or distance between this, right? Now you see the entire slab. This is the entire slab. Now this is minus Q and this is plus Q, and what is the separation between them? This is L. So I'll take this dipole moment as Q into L. Okay, Q into L. Now coming to the polarization, the definition of polarization states that it is defined as dipole moment per unit volume. So polarization is represented by the symbol P, dipole moment by volume. What is dipole moment? QL. What is volume? A into L. So it is nothing but QL, which is nothing but the amount of charge which has been developed inside the specimen per unit area is called as a polarization. The units of polarization of this is coulombs per meter square. Okay, and polarization is basically a vector, so that's why I have mentioned here as a vector. Normally, if you consider it as a scalar, this is the expression. Now, since it is a vector, I'll be taking this expression. Okay. Now, so having said this, as already, polarization is nothing but charge by per unit area. You know the charge per unit area, which is nothing but this is the developed charge, which was not there initially. This is a developed net charge per unit area. You know the charge per area is called as charge density, surface charge density, right? It is called as surface charge density. And these surface charges are appearing because of polarization, isn't it? So that's why polarization is also called as surface charge density of polarization. It is equal to surface charge density and is often referred to as surface charge density of polarization. Normally, surface charges are represented by the symbol rho, sigma. P indicates it is a polarized charges. Now, coming to electric fields. Now, as you have already seen, this is the field which I am applying. So I'll take the applied electric field as EA, and because of that you are getting some charges which are displayed here in both the directions. Now let us suppose this induced field is given by E dash. Whatever the final field which has been induced, it is given by E dash. So if I take E dash, it is nothing but, as already been said, we have done for different things, it is nothing but minus charge density by epsilon naught. Assuming that it is a unit vector. This comes from the Gauss law, isn't it? Do you remember this thing? So this is a modification of this one. So E bar is equal to minus rho P by epsilon, and there will be a unit vector along the length of the axis. Now this can be represented as minus P by epsilon, because this is a surface charge density. If you are still wondering about how you got this equation, we have already done them for a surface charge. What is the electric field intensity? You know the electric field intensity is normally given by Q pi 4 pi r square, right? Where this is a charge and this is the 4 pi epsilon r square, right? 4 pi r square is nothing but a surface charge, right? Sorry, surface of this charge. So charge by surface area, if I take it as sigma, I'll get this equation. This is the equation which I am employing here. But since it is due to negative, I have taken it as negative. Now since the charges are due to surface charge, sorry, polarized charges, I have represented the symbol rho. And since electric field is a vector, this is a vector, yeah. This is the formula. So this can be represented as minus P by epsilon. So this is the induced electric field and this is the applied electric field. So now what is the developed electric field? E dash plus EA, it is nothing but your internal electric field which is there now present inside. So this is applied, this is developed. So internally what is present right now? This plus this. Now EA I'll directly take it as this one. Now E dash I'll take it as minus P by epsilon. This is my internal electric fields. Now this particular expression now, I'll define this one. The new term which we will be employing till our final year engineering. This is susceptibility, which is defined as this is not ratio, this is ratio of polarization of a dielectric material to the internal field intensity. Now let us suppose if this is the specimen, charges have been developed here, polarized charges. So the extent of polarization to the developed fields is called as susceptibility, represented by this. It has no units. Okay, so coming to this, susceptibility, we have already defined it as P by epsilon naught, and we do already P by EI, ratio of polarization to the internal field intensity. And internal field intensity, we already know that it is EA plus E dash. So this is the equation. Now instead of this, I will write it as E dash is already equal to minus P by epsilon naught, and this, what I am doing now, instead of rho, what I'll do, I'll apply this susceptibility into EI. So I'll bring this to one side. So I'll take 1 plus EI as common. What I'll be getting, EI into 1 plus psi by E naught. So what is internal field now? EA by 1 plus psi by. This is the field which is developed due to the applied electric fields. Okay. Now, this particular term which we have developed with this is called as a relative permittivity. A relative permittivity of the medium. So it is also referred to as dielectric constants. In some cases you will refer to it as relative permittivity, in some cases it is referred to as dielectric constants. Okay, and it is a ratio of, so what is the ratio now? EI is equal to EA by 1 plus psi by epsilon, right? This is what I am calling it as epsilon. So if I write it as epsilon r is equal to EA by EI, right? So it is the ratio of applied field to the internal developed field in the material. So if you join epsilon r and epsilon naught, this is called as absolute permittivity. Product of. Now, I hope that now you are able to understand the concept of polarization. You are able to now describe the concept of polarization and determine the polarization in a given specimen. Thank you.